In today's video, we'll develop an understanding of how to draw reaction mechanisms for substitution reactions with benzene, namely friedel alkylation, acylation, and adding a halogen in the presence of aluminum chloride, Lewis acid. So we'll do that, and we'll also do a final example of how to draw mechanisms for electrophilic substitution. Now, before we get started, all three of these reactions actually have very similar mechanisms. But first, let's develop the understanding that a lone pair, typically negative likes to attack positive, but here are the ways that can take form. You want to look for a lone pair and then attack it to an incomplete octet where it's electron deficient, such as aluminum. And a lone pair also likes to attack hydrogens, just as how negative things like to attack positive hydrogens as well. And finally, bonds like to attack the carbocation. So these are all different ways of saying negative likes to attack positive. So let's start with friedel-Crafts alkylation, which will serve as a basis for the rest of the reactions. Now we have lone pair. If you're confused on an exam, you see this. The first thing you want to do is try to find where your lone pairs are, and then try to match it with aluminum, which has an incomplete octet. It's a Lewis acid. Okay, so then when you draw an arrow between two things, that makes a bond and also gives you charge separation. Now I've said that the bonds like to attack the positive things, so we're gonna break off this positive thing, and that will give us a carbocation, which will become the electrophile, and also a negative charged aluminum, which will become the nucleophile, which will be useful as we do our electrophilic substitution with benzene that I'll get to in a bit. Okay, so that's the foundation. If you want to add a chlorine in this presence to prepare the electrophile nucleophile, it's really similar. It's just like friedel-Crafts alkylation, except instead of the alkyl here, you're just putting another chlorine here. And this is the final nucleophile you produce. And the electrophile is a little different. You don't get a carbocation, but the benzene's alkene will want to attack this chlorine. Okay, so that if this one is attacked, this electrophile is attacked, this bond, okay, like I said, the bond likes to go to the plus sign, so this bond breaks off, and that's how you get this product. Okay, so then for friedel-Crafts acylation is really similar as well. Instead of the alkyl, you're putting a carbonyl on this side, and once again you form the complex with charge separation. Now the only important thing I want to point out here is you want to create an acylation ion, okay? Acylation ion, which will be the electrophile for your substitution. To do this, here's how you draw the arrows. Like I said, the bond that likes to attack the positive charge, just like what we've done already. But now there's a resonance here. You want to keep in mind that your oxygen can triple bond with this carbon in an acylation ion. So then we look for where there are lone pairs. Okay, so when you don't know what to do on an exam, when you're drawing arrows, start drawing out the lone pairs so you can identify what can possibly attack what, okay? So when you're confused on an exam, draw out the lone pairs, which will give you an idea. So this will actually contribute to a triple bond to give you an acylation ion that can resonance structure. That has a resonance structure. Okay, so one of the resonance structures has a plus on oxygen and the other one has a plus on carbon. And this will be your nucleophile. Okay, and another variation of that is instead of your acyl chloride, they can start with an acid anhydride. They can start with an anhydride. Now, it's all very similar. You still create acylation ions. The only difference is instead of just simple two arrows like this, you actually have to draw more arrows so that you produce your acylation ion like that. So we start from the left. The oxygen's lone pairs contribute to the triple bond. Okay, and then this double bond goes to this single bond goes to the other side single bond, and then this double bond goes on to the oxygen. So it's like drawing a Lenny face or something. Yeah, And that also gets your psyllium ions, which you will use in our example problem. How to do an electrophilic substitution, and in this case our sample problem will be an Friedel-Crafts alkylation. Okay, let's do this. So first we need to prepare the electrophile and nucleophile, and then we'll react those things with benzene. So first we want to draw out the lone pairs, which will attack an electron deficient atom or an incomplete octet. That will create a complex, because when you draw an arrow between two things, that forms a bond in between them and charge separation. Now the bonds like to attack the positive things, so that ends up breaking off and creating a carbocation, and you have your nucleophile too. So this is nucleophile, this is electrophile. Okay, and now let's react it with benzene. So benzene electrophilic substitution has two main steps. Step 1 is to let the bond, as I said, see, this little chart really comes in handy. We don't know what to do, think about this. The bond likes to attack the positive thing. So the bond in our the alkene in our benzene will want to attack this carbocation. As a result, you now have this, okay? But be careful, sometimes there might be carbocation rearrangements depending on how complex your R group is, okay? So that means if our thing got substituted here and there's no more double bond here, that must mean there's a carbocation, okay? And now, this is step 1, okay? Step 1 is adding the electrophile to make a carbocation. Okay. Now step 2 is an elimination reaction. Okay, elimination 1 because of the carbocation, and this is a step where you lose the hydrogen, so then you revert back to a benzene. So then this negative charge so this negative charge can attack the H. Okay, so notice it does not directly attack the positive charge because this is an elimination reaction, so it actually goes through an H, which will give up its bond to create an alkene. So that's how you get your benzene ring back and with your new branch produced. Now I realize I just made a mistake. There are 5 carbons here, but now here it became 4 carbons. So let me fix that real quick. So we're just gonna add an extra bend. But now here is a challenge. See, this is on a primary carbocation, which is no good. Let's do a carbocation rearrangement, putting the methyl here and putting my carbocation here in the center. Now we have a tertiary carbocation. So then the thing we add at the end will actually be, okay, so it will attack this region. So we will have, here, let me draw it like this. 1, 2, 3, 4, like that. And that will be the right answer. So this is a good learning experience for everyone. If you have an extra bend here, don't lose the extra bend. And so yeah, so this is your Friedel-Crafts alkylation reaction. And you notice that you create the carbon bonded to the benzene being a tertiary carbon. So the Friedel-Crafts alkylation is good for secondary and tertiary carbon directly bonded to benzene, whereas if you want to create a methylene primary carbon bonded to benzene, I have another video on that.